All right, welcome back to the world of fractions. You've probably seen the last video. This is part two. You are at the point now where we were working with whole numbers and everything, but now we're going to talk about parts and things that aren't whole numbers. Still in the positive, but yes. Fractions. I have, let's say, a perfect square. Pretend that it is. I know it's not. And I wanted to split it into two equal parts. The question becomes, how do I represent each part? Because it's kind of unnatural to, well, you're splitting something down and you're going to just count the groupings. Doesn't really make sense. So I literally take the whole, which is one. I have one whole object and I divide it into two equal groupings within itself. So I have one half and another half. And these are two equal groupings. And hint and cue for you, fractions are essentially division. Just keep that in mind for the future. Fractions are essentially division. You are dividing a number into equal parts or groups, just like division. So that is what division is. Now, likewise, I have a whole square and I want to split it up into four parts instead. So likewise, I take the whole square and I divide it by 4. And each of these are a quarter, right? A half, a quarter. Now, notice a couple things. If I add the two halves together at the top, for future reference as well, you can add fractions together with the same denominator. So you'll be left with 2 divided by 2, 2 over 2, and that is 1 because 2 divided by itself is 1. Any number divided by itself is 1, with the exception of 0. That is a far future lesson. Same thing if I add all 4 parts together, they will also be 1, starting from 4 divided by 4, and then it simplifies to 1 because a number divided by itself is 1. Now we'll dig into some examples, and I will even add something so we can sort of get our operations going. There's going to be more. I still have to write the backside. So a half plus a quarter. As I said, you're adding. You can only add fractions that have the same denominator. So one of these has to change so that we acquire what is called the greatest common denominator. So you find a common denominator and you can add these together. The way you do that is essentially, there's a little trick. In this case, I can make 2 and change it to 4 for that denominator. So it is with this little trick of, if you remember the special rule of a number multiplied by 1 is itself. So I can change 1 and I can change it to be this, 2 divided by 2, because as explained just now, a number divided by itself is 1. This is the same. What's going to happen essentially is, and I'll write this on the side, the denominator is going to multiply and change to 4. The numerator is just going to change to 2, because when you multiply fractions together, the top multiplies and the bottom multiplies. 2 times 1 is 2, 2 times 2 is 4. So you end up with 2 divided by 4 plus 1 divided by 4. 2 over 4 plus 1 over 4, which makes sense, right? 2 of these quarters is 1 half, right? You see that, like, it's just split one more time into another set of equal parts. That's all it is. That's why it makes sense, and visually you can see that. So your answer, therefore, is 3 over 4. Again, makes sense. You have 1 half, and you're adding one more piece to it. Cool. Now, a little more complicated, right? 2 over 7 plus 1 over 3. Or if you want to be fancy, 2/7 plus 1/3. Same thing, except Now it's not as easy to find uh, the greatest common denominator because you're gonna have to be messing with both fractions. Same trick, just you got to do it with both of them. So what I'm gonna do is essentially I multiply this by 3 over 3, and I multiply that by 7 over 7. Because, like I said, I want the denominators to be the same. The only way I'm going to be able to do that is multiplying them together. And apologies for the poor handwriting. I got a Sharpie hoping it would be a little bit better, but it's kind of weird. My handwriting is not the best, but I digress. 6 over 21, see if I can squeeze this in here too, plus 7 over 21. And then that adds up to be, quick little interruption here. I wrote 11 over 21 and I was scrubbing through the edits and I felt stupid. So I recorded this to tell you I corrected myself. 11, I'm going to shorthand this, over 21 as your answer. Again, it's 13 over 21. And I'm going to circle this too as that so you're not confused. So that's our second answer. So it's a matter of changing the denominator. Right? 1/3 minus 1/4. I'm gonna veer here a little bit. So same thing. I want a common denominator because otherwise I can't operate addition or subtraction. Multiplication, division is different. So we're gonna get into that next. 1/3 times 4 over 4 minus 1/4 times 3 over 3, right? We're essentially swapping. So this changes out to be 4 divided by 12 minus 3 divided by 12, which I'm left with, hopefully you can see that, that's a 2, which I'm left with 1 over 12. And that would be my answer for this. Up to operations again, so. Okay, as promised, more operations, right, with fractions. Pretty much you kind of got the idea of it, hopefully, to this point. Multiplying fractions together, you are literally just multiplying the numerator with the other numerator and the denominator with the other denominator. So that becomes a fraction of 5 times 7 over 9 times 10, which gives you 35 over 90. There is something else we can do with this, so we will come back to this. Little asterisk there. Dividing fractions, which I'm going to be honest with you, you will never really often see this notation as you progress into the higher maths. But it is the same idea. You are dividing the numerators and dividing the denominators. So you are left with 3 over 5. Now, I said we're going to come back to this because there's something else we can do with that. This fraction can be broken down further into its simplest form. We call it simplification. Right now, I'm seeing something in this fraction that can be, essentially it can be divided out. The way you figure that out is by factoring. So I'm going to do each of the numbers here. We're going to do the numerator first. We have 1, 5, 7, and 35. Those are all your factors for 35, right? And reminder that these are what multiply to 35. They're the pairs, respective pairs. 90 has quite a few more. List them out. 1 and 90. I'll go further. We've got 2 and 45. We have 3 and 30. We have 5 and 18. And we have 9 and 10. I think that's it. I'm pretty sure it is. Hopefully I'm not wrong there. But this has a bunch of factors. Notice though that I have 5 and 5. So we're gonna use that to our advantage. So back to this thing here, 35 over 90. What you're gonna do essentially is you're going to split it apart. And I'll do it. Oh, excuse me. I got screwed up. I'll do it my way first, and then I will show you the other way you could do it based on what was here earlier. So you have now, you split into factors of 7 and 5, right? Because we know those are factors. And you split this into 5 and 18. So now, right, using our little noggins here, this is also equal to this. Because, right, multiplication, if you're just multiplying things, you can flip them around. I'm not gonna get into the formal jargon of, you can probably look it up. I think it's either I'm pretty sure it's the communicative property. I hate talking about that because it confuses people. I just don't prefer to talk about it. Let's just say that multiplication, you can flip things around, right? And technically, right, this can also be represented as 7 times 5 over 18 times 5. That is the same, right? That's essentially what that property is. I don't like going over that because it's just too much talk. Essentially, I can single these out because, hey, it's the same as multiplying different fractions together. You can just split the numerators and denominators apart. And then I'm left with that statement there of 7 over 18 times 5 over 5, which you already know 5 divided by itself is just 1. So your most simplest, I know I'm kind of all over the place, your most simplest fraction, therefore, is 7 over 18. Now, I told you I'd show you a different way because you might have chosen different factors. That's still fine, right? So I got 35 over 90. You might have chosen, okay, well, 7 over 5, 7 times 5, excuse me. And then you chose maybe 9 times 10. That's perfectly fine because guess what? 10 also has factors. You might just expand it a little more, but you end up with 7 times 5. And then you have not, really, if you wanted to factor 9, that's fine too. You could do 3 times 3, and that, it equates to 9. But then you break down 10, and it's 5 and 2, right? Because 1 and 10 aren't really useful. You still find the same result here that, hey, well, regardless, it's being multiplied, and you can still essentially rephrase it to mean the same thing. So you'll basically have this whole expression, and then all of that multiplied by 5 divided by 5. You'll find that the bottom is going to be the same. You're gonna find it up to 18 because you can't break this down any further. All these are prime numbers. So this is 1 yet again, and then all these multiply, and you're left with 7 over 18 yet again. Again, questions, if you have any, decimals. And this is where, again, kind of the hate for math starts is, oh, well, why do I have to learn this, right? So decimals kind of starts out with your knowledge of the place values, right? I have like sample numbers here, right? You have 198, for example, right? Well, what does that mean? I have 100 plus 9 of the tens place, because that's 90, right? Essentially. And then I have 8 ones, which is 8. So essentially, right, obviously, if I were to count like, 199 and then go to 200, right, this will go back to 0, but this will go up a place, that'll go up a place, and it'll be 200. So now, like, yeah, you add up, you get another place value, essentially, in the hundreds. 22, you have 2 tens and 2 ones. And likewise, if I just had 7, it's just 7 ones. Decimals come in essentially on that same logic of powers of 10. We say powers of 10. I'm going to show you why. I'm going to draw it out. But essentially on the notion that there are places beyond the ones that are fractions of 10 and powers of 10, really. So, for example, 0.1. 198.1, right? Well, if this is the ones place, well, if I divide 10 more on top of that, this becomes the tens place. And we will represent it. I'm going to draw it in here in a minute. I'm going to edit it and show you. Okay, so I've drawn this now to kind of give you hopefully a visual, right? Representing each place value, right? And let's go back. Let's even go back to our example, right? We had 198, 1, 9, 8, and then point, right? The decimal, 0.1. And even for funsies, I'll add another one. Let's do 2 there. You can see why. So if you notice, right, as you're going right to left here, and you're going up, right, you're increasing by essentially increments of 10, and you're multiplying this by 10 to get to the next place. So starting from here, even like, right, this is 1. Well, what is this place really, right? It's 10 to the 0th power, right? Which, by the way, I forgot to cover that in the first video. That's a special case. Anything to the 0th power is 1. I forgot to mention that completely. I'm just now thinking of it. But moving on. This would be 10 to the 1st power. This would be 10 to the 2nd power, because 10 to the 2nd power is 100. 10 to the 1st power is itself 10. So as I move down, right, this pattern becomes 10 to the negative 1st, which we have not gotten into yet. We're going over negative values next time, and we're going to kind of segue into exponents and whatnot too. And this is 10 to the negative 2. I know I might be getting ahead of myself, but essentially it's to show you the pattern. Some of you might already be familiar with negatives, so that's why I'm kind of throwing it in there. But these are all fractions of 10 in one way or another, or multiple. You get the point. Very weird to explain. I can't really get it across. But if you see that diagram and you understand it, you see what's happening. So, right, this is therefore, it's not the tens place, but the tenths place with a TH at the end, THS. And this is the hundredths place. That is why we name them that. That is why we name them those places. 1/10, 2/100ths. As long as you know that, you really don't have to be naming them that. We typically just say, okay, 198 or 198.12. It's acceptable. No one cares that you say it formally, as long as you understand what it is, what place value it holds. No one really cares in the higher maths what you call it. It really doesn't matter. yes, have that understanding if it was ever brought up, but you don't have to call that all the time. So just as a heads up. Okay, post recording edit. Actually, I had to re-record a clip here. I lied to y'all when I said that was the last thing. So you probably saw it was kind of blatant and abrupt when I cut out the thing about decimals, right? There's one more thing that relates to decimals and fractions, and it is super important to understand, and that is percentages. Percentages. What is a percentage? Percent literally means out of 100, right? A century, centennial, right? That means 100 for those of you. That's what that word, or at least that root of the word means. Percent just means of 100, out of 100. So typically we like to use percentages as well to represent parts of a whole, right? The easiest, right? Let's say I have 100 of something, right? This is the easiest to do because obviously it's 100. So if I were to ask you, what is 100% of 100? 100% of 100. 100% means it is the whole thing because it is out of 100. That's the whole thing. So it's 100. Okay. Well, if I were to ask you, what is 25% of 100? Like I said, starting real basic, it seems clumsy, but right, that'd be 25 because out of the 100, the quarter amount is going to be 25. Hint there too. I kind of got ahead of myself, but 25% of that is 25, and you'll see why it's a quarter. And if you look at this, right, of is pretty much a word meaning multiplication. So even if you were to visualize this in a different way, it's really just 25 over 100 times 100, which if you do the math and remember, if I rearrange this, it ends up being this, right? 25, and then you have 100 divided by 100. You know that this is going to be 1 because it divides by itself, so you just have 1, and you're left with 25. So that's the other way of looking at it. So when you see this, it really is just a fraction out of 100. That is literally it. And is of 100, right? Now I can throw the question at you of, okay, let's do just a random number off the top of my head. Let's do 25% of 40. Just off the dome, right? Just to kind of show examples. 25% of 40. Okay, cool. Well, 25 over 100, because that's what a percentage is. Oh, and by the way, I probably should have led with this too. You could absolutely do this and simplify, and this cancels out and it becomes 25. This is a quarter when you simplify this, because 25 goes into 100 4 times, and 25 goes into itself once. So that simplifies to a fourth. So right off the dome, right, I'll multiply this, but in this next line, right, I know this is a fourth when I simplify it. It's a fourth times 40. So really, what's a quarter of 40? Oh, and look at that. It's just a basic division problem. It becomes 40 divided by 4. Because I'm not adding, I'm multiplying a fraction and a number together, right? 40 divided by 1, technically that's still a fraction, but it becomes this. 40 divided by 4 is 10. That's it. That is a quarter of 40. Makes sense. And if you want to, backtrack and check your work, right? 10 divided by 40, you simplify that, hey, it's a quarter. Bam. There you go. Now, not every problem is going to look this neat. Like I said, I'm just providing the examples so you understand the concept.